All right, so my name is Isaac Wolstenholme, and I'm going to be talking about heterojunction tunneling field effect transistors. So let's get into it. Okay, so this is the article. This is the title: Fabrication, Characterization, and Physics of 3,5 Heterojunction Tunneling Field Effect Transistors for Steep Subthreshold Swing. So, yeah, it's a long title, but yeah, not trying to bombard you with information. So here are all the authors. Came from a group from Intel. Pretty cool. All right, let's move on. So in learning about this technology, I find myself being reminded a lot about Zener junctions. So I'm going to talk about a Zener junction real quick first. So a Zener junction is just a PN junction. It's a special kind of PN junction. It's just heavily doped on one side. Let's say we'll heavily dope the P side. So that's what it's going to look like. It's going to look like something like this. Here's the N side. It'll be steep bend down right here by the junction, and then it'll be kind of gradual on the inside. All right. Okay, so cool. Why do we care? Well, if we apply a reverse bias like this, then this thing is going to move down, right? You're going to have Fermi levels. Everything's going to be out of equilibrium. This is the Fermi level. You're going to get quasi-Fermi levels, right? So we clear this. It's going to look something more like this. Here's the Fermi level on the P side, Fermi level on the N side. Something like that, right? And so then, let me draw this a little bit better, actually. I'm sorry. Just really killing my time here. So yeah, so this, you'll get tunneling across this little junction right here if you apply reverse bias, okay? So it has to be sufficiently high enough. If you don't apply high enough, you won't get tunneling. So that right when you get enough, it's kind of like a threshold. They don't call it a threshold. They call it a nominal voltage, right? So this is the minimum voltage between these two levels, so that tunneling starts to occur. It's called Zener breakdown. So, okay, let's talk about the basic tunneling field effect transitions before we get into the work of the paper. So a tunneling field effect transistor is just, well, the way that they have it. They have a heavily doped P region, heavily doped N region over here, and they have an intrinsic bulk material. That's the semiconductor part of the device. And then the rest is pretty standard. You just got an oxide layer. It's about what you would expect. It's a field effect device. So then you got a gate. Okay, so taking this to be the source over here. This is the drain. This is the gate. Okay, so now let's just think about a band diagram across the channel right here. All in equilibrium, 0 gate voltage applied. So we got a flat Fermi level over there. And then here's our P-type conduction, or I'm sorry, valence band. And then it dips down into the intrinsic level. The intrinsic Fermi level is mid-gap, right? And then you have a kind of gradual, and then it gets really sharp in the N region, right? And then sharp transition here. It's kind of gradual. There's the intrinsic region, and then kind of gradual, and then sharp, right? So you get this kind of like staircase. The scale is maybe a little bit stretched vertically. It's kind of tall, but you get the idea, right? So let's see. If we apply, obviously we're not going to have any current going this way right now, right? But if we apply a gate voltage, right? If we apply a gate voltage, if we just think about our MOS capacitor, if we apply a positive gate voltage, then the oxides can do something like this. This is going to be lower, right? This is going to be higher. Positive gate voltage over here with respect to this side, right? And so you're going to have holes getting it repelled and electrons getting attracted over here, right? So this is intrinsic, so the Fermi level is going to be in mid-gap, but then you're going to have band bending due to the higher concentration of electrons on the interface. It's all going to bend down, right? The conduction band is going to get closer to the Fermi level. Valence band is going to get further away. That's from those fundamental equations we learned about, talking about concentration of electrons and the concentration of holes in the valence, in the conduction and valence bands respectively. You know, NV times exponent, blah, 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 NC times exponent. Right? So yeah, you can think about it like that, right? So basically what I'm trying to say is if you move this way and you have a gate voltage applied, right? If you have a gate voltage applied and you're moving this way, this conduction band edge is going to get closer and closer to this Fermi level, the closer you get to this interface, right? So when you get right close to the interface, with that gate voltage applied, right? Let's see how fast I can erase this. What you're going to get is still no drain voltage applied. You're going to have something like this. Right? And so then this region is pretty much all N-type, right? And so now what we can see is over here, this looks a lot like a Zener junction, right? So if we apply a high enough drain voltage here, it's going to reverse bias it. You'll start to get tunneling over here. You'll get a conventional current in this direction. Electron current goes left to right. Conventional current goes from right to left. So yeah, pretty cool. Just another way of making a transistor. So, I mean, that's all good and nice. What are the benefits from it? And so this group, I guess, made the subthreshold swing of this device unusually low. And so this article was published in 2011, so it's relevant to 2011. But yeah, so this is a picture taken from the article. This is the part I just drew for you right there. And this is the part that they're interested in. This is the part they added right here, this little layer, indium gallium arsenide pocket. And this particular composition of indium gallium arsenide has a different band gap than the rest. So it's a heterojunction. So that's what heterojunction means. It just means that it's a material with a different band gap than the rest of the material. So if we did go to the next slide, we'll see what that does for us. So here's the homojunction. Homo meaning the band gap is the same throughout, right? Hetero, you can see there is a little change in the band gap right here. It's lower, right, in this pocket right here. And so that allows for the tunneling barrier to be lower, and so you get a higher current. That's it. So on the next slide, why do we care about this? On the next slide, subthreshold swing, right? We talked about this beginning of Unit 4. So if you got a digital device, right, and you've got a gate voltage varying and your drain voltage is fixed, the question is, how does this current behave? The important questions are with digital circuits is how big is I? How big is the current when VG is low, say 0 volts? How big is the leakage current, right? The other thing to consider is when we change VG by a certain amount, how much does I go up? Both of those are important quantities. So we want the change in I for a change in VG to be large, and we want the leakage current to be very low. So the subthreshold swing is a way of measuring these two kind of things. So we look at the minimum current when VG is 0, and we look at the slope of this graph. This graph is a logarithmic scale for the drain current and a linear scale for the gate voltage, fixed drain voltage, and you just vary the gate voltage and you measure the current. And so on the left, this is for homojunction. You see the subthreshold swing is the inverse slope of this graph, right? So it's millivolts per decade. So it's 77 millivolts per decade. It's basically just how much the gate voltage swings to go from the off state to the on state. Okay, that's where the name kind of comes from. So over here, you can see it's much lower. You don't have to swing the gate voltage as much to go from one state to the other. So that's a good thing. That's the main result. That's why this device is worth noting. It's because it has this low subthreshold swing. So yeah, one thing to notice is the oxide thickness is also different. Over here with the homojunction, it's 14.5 angstroms, whereas in the heterojunction, they got it down to 11 angstroms. So that's also playing a role. Obviously, if the oxide thickness is thinner, then you have less screening of the electric field on from your gate, and so you have a more prominent channel forming earlier with a thinner oxide layer. So that's also playing a role here, so not to be ignored. So yeah, pretty cool. This was, again, published in 2011, so I'm sure there's much better results now, but very interesting device technology. So also one thing worth noting here is the leakage current through the gate. With a low drain voltage, it starts to happen earlier. And, you know, that makes sense. If we just look at a device here, And if we have 0.8 volts on the gate, as shown here, but we only have 0.05 volts on the drain, right? This difference is pretty large, right? It's about the same as it is down here on the source. Versus if this was 0.3, right? If this is 0.3, then this difference is much smaller than over here, right? So you have less of a tendency for a current to go through that gate interface. So yeah, anyway, I hope you enjoyed my presentation. I sure had a good time learning about this technology. It was very interesting. And so yeah, thank you very much. And I hope you have a good day. Bye-bye.